Alright, this next one's really interesting. We've got a device here, and it says the photoelectric effect, Planck's constant. So this device is, I would guess, several decades old, maybe 50 years old, at first glance, just looking at the packaging. And basically what it is that on the back here, you've got this aperture. I say the word aperture just means a hole that light can go through. And so on the back here, there's actually a light, and you can slide that light in like so. And so that light is going to pass through the aperture. And then on the other side of the aperture, so remember that the aperture is here, so that's where the light is coming through. And then you've actually got a place in there, you can see that, and you can actually put these slides. These are actually filters. So the reason why this appears green is because it only allows green light to go through. And actually that's a bit of an oversimplification. It does allow some other wavelengths to go through as well. It's not just 100% a certain wavelength, but that's roughly what it is. And what we do is we actually assume that the frequency of light that corresponds to green light is actually the maximum frequency of light that is allowed to pass through this. So we can put that filter in here, we close this door, and now we're going to have light passing from the back through that filter. So we're going to then have green light, and then right here there's actually a phototube. Okay, so the phototube is actually there's a diagram of it. There we go. So that's what the phototube looks like. Just is very small. It looks a bit like a light bulb. And you can see that there's basically a prong that comes up in the center of it, and then there's this sort of semicircular material that is behind it. So what's going to happen is that the light, so remember that it's got this glass tubing on the outside, so the light, that in this case green light, is going to pass through that glass, and it's going to hit this cathode material here at the back, and it's going to cause electrons to be released. So that's the cathode material at the back. That's that semicircular one. And once those electrons are released, they're going to start, or if they're emitted, they're going to travel across to this prong here, which is the anode, and ultimately that's going to complete the circuit. Now there's a bit of an issue. You might say, but wait, won't the light also hit the anode material, that prong that sticks up there? Won't it also hit that? And the answer is yes, it will hit that. And that's why there is, if you can see on this diagram here, but there's actually a shield on the front side of that anode material. So this is where the light is coming from, and so it's going to go this way, and then there's a shield there to prevent the light from hitting that material. And so instead it goes around, it hits the cathode material here, and then the electrons are emitted, and then there's no shield on this side here, and the electrons flow across here, and we actually get what's called the photoelectric effect. We get what's called a photocurrent. That's those electrons that are emitted and they flow across. So the current that we're going to get is going to be very, very small. It's going to be on the order of nanoamps. So there's actually a nanoammeter inside here. So it's actually a fairly simple apparatus. The light comes in the back, passes through a filter, then there's the phototube here. The light then hits the cathode material. If it has enough energy, it can emit electrons. They then flow across to the anode, and then there's just a completed circuit here, and within that circuit there's a nanoammeter which measures the amount of photocurrent. Now the last piece of the puzzle is that there's also a backing voltage that can be applied. So there is a power supply section of this circuit, and we can actually then adjust that to apply a voltage in either direction. But in this case here, it's specified that it's actually a backing voltage, which means that it's going to actually oppose the flow of photocurrent. So what that's going to do is that if we get a photocurrent that is flowing, if I turn that backing voltage up high enough, it's going to actually send those electrons back where they've come from. So the power supply is actually connected to the anode and the cathode. Now remember that the electrons want to flow, and that's when we get a photocurrent, they're flowing from the cathode to the anode. Now if I made the anode negatively charged, that would actually repel the electrons back. They wouldn't want to go there. Okay, and if we also, in not just making the anode negatively charged, also making the cathode positively charged, well, even if the electrons sort of have enough energy to be emitted, they're going to be attracted back to that cathode. So that's why the backing voltage will actually stop the flow of electrons. Okay, so it just has to do with the attraction and repulsion between the different charges. So what we can then do is we can actually measure, so we would actually adjust this knob here, and we can actually measure what that backing voltage is, and we can use that backing voltage to then calculate the kinetic energy of the electrons. So it's really a nifty experiment. So I'll just set it up and run through just one trial with it. Now, keep in mind that if you wanted to do this experiment legitimately, you want to reduce the possible sources of error, you would do this in a darkened room. So ordinarily when I get students to do this experiment, they would do it in a darkened room. There would be no light. You don't want there to be any sort of risk that we can get excess light contacting the cathode, because that could alter the results. So you do it in a dark room, but this is just for illustrative purposes, so I'll do it in a light room. If I turn the light off, then it won't be possible to see anything on the camera. So I've still got the green slide is still in there, so I'll go ahead and close that up. This is just the power knob here, so I'll turn that to 1, and what's being displayed on the screen right now is the photocurrent. Now remember that this is in nanoamps. Actually, this one's in nanoamps, this one's actually microamps. So this is actually in nanoamps right now, and I can see there's about 0.1 nanoamps. That's what it says on the screen. 0.1 is what it says. So even just that little tiny amount of light that's making its way in there is causing a very, very small amount of current to flow. Now if I actually turn on the light inside, so I'm going to turn the backing voltage all the way down. There we go. So it's got this sign here, and initially I thought that was a negative sign, but it's actually an arrow that points to the left, and apparently that arrow that points to the left means it's got low battery. So don't take that as a negative. That's just ignore that sign there. So you can see right now, so the light is on back there. We're getting green light that's hitting the cathode, and we can see that we are actually getting current that's actually flowing, photocurrent. And we can see that the amount of current it's oscillating between somewhere between about 14.5 and 16 nanoamps. So again, if you do it in a closed environment, a dark room, you put it on the table, you're not sort of jostling it around, etc., you'll actually get a very consistent reading. You won't get all this oscillation like we're getting here. Now, what I would do is I would write down the wavelength of the light that corresponds to this green filter. That would be given by the company that makes the filters. And I would then know the frequency of light that's hitting the cathode. I would also then adjust the backing voltage. And you'll notice what happens, I'm turning the backing voltage up, and you notice that the current, of course, is going down. Remember that the reason for this, and eventually it'll go down to 0. And the reason for this is because we're actually negatively charging. So we're giving a negative charge to the anode, which is actually repelling those electrons back the direction they came from. So now we want to get it to the point where it's just at 0, and I can see it's basically all zeros. And sometimes you get a little 1 in that decimal place there. But essentially we've stopped the flow of current. So this is what we would call the stopping voltage. Now in order to read what that stopping voltage is, we'd actually just turn this knob to the right, and this reading on the screen, which is it 0.825? I guess it's actually just changed a little bit, but 0.824, 825. So that's going to be the stopping voltage for green light with this particular cathode material. So what that tells us is that, if you remember, that's our stopping voltage. Now the relationship between stopping voltage and kinetic energy is that the kinetic energy is going to be the same value as the stopping voltage in electron volts. So in this case here, if it's 0.824, that means that the electrons are going to have 0.824 electron volts of energy. So this is what you would do with this apparatus, and you could put a different slide in there. So you could take, let's see what we've got here. So we've got a yellow one. So I could swap out the green one, and I can put this yellow one instead. So we're going to get yellow light now hitting the cathode. And so the question is, well, is yellow light going to be more or less energetic than green? So if you remember the spectrum, so it goes Roy, J-Biv, right? And so of course the R part is less energetic, longer wavelength, lower frequency, lower energy. And the V part is actually lower, smaller wavelength, higher energy, because it's got a higher frequency. And we can see that, that the yellow is actually going to have less energy. So what we'd expect is that the stopping voltage then should be less. Now, is that the case? So let's go back to the current. So now there is actually a negative sign there. Okay, so there is a negative sign there. Now, what's going to happen is that's because my backing voltage is actually too high. It's actually sending the electrons back to the cathode. So I'm going to just adjust that down a little bit. So now it's gone back into the positives. Adjust that down as close to 0 as possible. There we go. We've now found the stopping voltage, and we can read that stopping voltage off, and it's 0.777. So the green one was 0.824 electron volts, and the yellow would be 0.777 electron volts. So that's what you would do with this device. So very simple. You would just put a slide in. You would write down what the wavelength of light is that is allowed to pass through that slide. What's the frequency that's associated with that wavelength? Then what you would do is you would then adjust the backing voltage until the point where it's at 0. So you want to find the point where it's just at 0 because that's going through the stopping voltage. Then we turn it over, read off what that stopping voltage is, and that's going to then give us the kinetic energy of the light. So from that, we can create a kinetic energy versus frequency graph. And remember that the gradient of that graph is going to be Planck's constant. So we can actually get an experimental value for Planck's constant. I've actually done it several times using this device. You don't get a perfect result, and there's a reason for that. That'll be something to think about. But usually we get a value that's somewhere around 3 times 10 to the negative 15 electron volts seconds. So a little bit off of the 4.14, which is the accepted value. So it's off by about 25%, and that's something that we can try to figure out why. Why is it off by 25%? So that's the photoelectric effect apparatus.